Oh, hi. Fancy meeting you here again. So, just recently we talked about the hallmark of this course, the fundamental theorem of calculus. Super exciting stuff. Now we're going to talk about the second fundamental theorem of calculus. Oh man, the second FTC. Are you serious? There's two of these things? All right. This one, the sequel is never better than the original, but let's see if this one holds up. Okay, so I want you to imagine a function. I'm going to call it capital F of x, and it's equal to the integral from 0 to x of t squared minus 3t plus 2 dt. Okay, this is kind of weird, but I hope you agree that this is in fact a function of x. Let's maybe verify that. How can we do this? So I've got here a definite integral, right? I've got an integral from 0 to x of some function. So the way that I do this is I would need to find the antiderivative of this function. Typically I've been calling the inside function little f, so little f of t would be like t squared minus 3t plus 2. And then I call the outside function capital F of t. But here that's not really going to work for me because I'm already using capital F. That might be a little bit confusing. So maybe I'll call it, I don't know, capital G. Is that okay for people? The antiderivative of t squared minus 3t plus 2 is, of course, 1/3 t cubed minus 3/2 t squared plus 2t. Okay. Again, typically we put a plus c, but we're doing a definite integral now, so you don't need to add 0. Okay, so that's what my antiderivative is. What I'm going to do is I'm going to plug in x to this function. I'm going to plug in 0 to this function and subtract the results. Clearly, if you plug in 0 for t, you get 0 out. And if you plug in x, you get 1/3 x cubed minus 3/2 x squared plus 2x. Okay, subtracting those two things, obviously subtracting 0 does nothing for you. So I believe that capital F of x, another way of writing this, is just 1/3 x cubed minus 3/2 x squared plus 2x. Okay, so this function is in fact a function of x, and it's because, I mean, we're integrating a function with respect to t, right? And that means you're finding an antiderivative. But then when you plug in 0 and x for t, then you're going to be getting a function of x out. Okay, this is a little confusing. There's a lot of variables going on. Okay, so I've simplified what f of x is equal to. My question, though, is what is f prime of x? Capital F prime of x. Well, I mean, this is just, differential calculus that we've been talking about all year long. Take the derivative of this, and we get something like 3 times a third is 1, x squared minus 3x plus 2. Okay? So I started with a function, capital F of x. Capital F prime of x was x squared minus 3x plus 2. Okay, cool. Who cares? Let's move on. What if instead of having a lower bound of 0, I have a lower bound of 2? So we do kind of the same thing here, right? So capital G of t, the antiderivative, we just did this a moment ago, is 1/3 t cubed minus 3/2 t squared plus 2t. I'm again going to plug in x, and I'm also going to plug in 2, and I'm going to subtract those results. If I plug in x, I get the same thing, 1/3 x cubed minus 3/2 x squared plus 2x. When I plug in 2, that's more complicated. I get some number. I don't know what number. I don't really care what number, but I get some number. So when I subtract these, capital F of x, another way of writing this, is going to be 1/3 x cubed minus 3/2 x squared plus 2x minus whatever that number was. Why do I not care about what that number is? Correct, because I'm asking for f prime of x. I'm asking for the derivative of this function. And the derivative of whatever number that is going to be 0. So when I take the derivative of this, I get, again, just like in the last problem, x squared minus 3x plus 2. Huh, interesting. Interesting. I wonder what happens if I integrate from a to x, where a is any number. What do you think we're going to get? Do you think we'll get the same answer? I think we will too. I think we're yet again going to be getting x squared minus 3x plus 2. Are you all seeing what's happening here? Are you seeing the magic that's happening here? We started off with an integral of something with t's in it, t squared minus 3t plus 2. When you take the derivative of that integral, you're getting x squared minus 3x plus 2. Huh. Coincidence? let's see. Let's try another example here. Let's suppose that a is any number that you possibly imagine. I want to define my capital F of x function to be the integral from a, whatever that number is, to x of this function, sine of t plus cosine of t minus e to the t. So again, I could take this inside function to be g of t, right, like little g of t, and then capital G of t would be the antiderivative of that, which would be what? Negative cosine of t plus sine of t minus e to the t. And then I'm just going to plug in x, I'm going to plug in a, and I'm going to subtract those results. So when I plug in x, I get negative cosine of x plus sine of x minus e to the x. And when I plug in a, I get, well, just some number, right? Whatever a happened to be, I'm going to get cosine of that number, which is a number, plus sine of that number, which is a number, minus e to that number, which is a number. So I'm just going to get some number. So when I subtract them, capital F of x is just negative cosine of x plus sine of x minus e to the x plus some number. What's f prime of x then? Just the derivative of that we're going to get. The derivative of negative cosine is sine, the derivative of sine is cosine, and the derivative of e to the x is e to the x, and the derivative of a number is 0. Oh my goodness, this happened again. My inside function was sine of t plus cosine of t minus e to the t, and my derivative of the integral was sine of x plus cosine of x minus e to the x. How magical. My goodness. Hope you're seeing what's happening here, folks. This is exactly what the second fundamental theorem of calculus gives us. It says the following. If your original function, capital F of x, is the integral from a to x, where a is any number, and x is your variable, you're integrating the function f of t dt, what do you think f prime of x is always equal to? Correct. It is always going to be equal to just simply f of x. You basically just replace all the t's in your function inside of the integral here with x's. Oh, that's so nice. Intuitively, I hope this makes sense though, right? We're taking the derivative of an integral, which in other words, we're taking the derivative of an antiderivative. And so those two things should sort of undo each other, right? Think about your inverse functions. Inverse functions, they undo each other when you compose them with each other. Here, if you differentiate and then integrate, or if you integrate and then differentiate, you're sort of undoing what you just did. So you should get back to what you started with. Some things to consider, which we're going to talk about in class, are the following. What if my function wasn't just from a to x? What if it went from a to some function of x? So my upper bound is g of x. G of x could be like x squared or cosine of x or anything else. I wonder what f prime of x is now. Similarly, I want you to think about this. What happens if both of my bounds are functions of x? I don't have any constants here. So I'm going to integrate from g of x to h of x. I wonder what the answer is going to be for this too. Something to discuss in class. All right. Thanks for tuning in. Hope you enjoyed this, and I'll see you all very soon.